In this video, we discuss product to sum and sum to product formulas. These formulas turn out to be particularly useful in integral calculus. Although we will illustrate some examples now, the motivation for why we'd want to make some of the substitutions may not be clear until future courses. We will start with the product to sum formulas as they derive directly from the addition and subtraction formulas. We will state the formulas and show the proof of one of them before we consider specific problems in which the formulas are used. First, we have that sine A times cosine B equals 1/2 the sum of sine A plus B and sine A minus B. Next, we have that cosine A times sine B equals 1/2 the difference of sine A plus B and sine of A minus B. Notice the similarities between these two formulas. We can derive the second formula from the first, knowing that sine is an odd function and that B minus A is the opposite of A minus B. Also note that these two formulas have mixed factors, one sine and one cosine, but the sum formulas use only sine. Next, we have cosine A times cosine B equals 1/2 the quantity cosine A plus B plus cosine A minus B. Finally, we have that sine A times sine B is 1/2 the quantity cosine A minus B minus cosine A plus B. Again, notice the similarities between these last two formulas. Both have factors with the same trig function, and the sum formulas use only cosine. Let's consider the proof of Formula 4. The other proofs are quite similar. We start with the formula for cosine of A minus B and the formula for cosine of A plus B. Subtracting these two equations, we see that cosine of A minus B minus cosine of A plus B on the left-hand side, and we get 2 sine A sine B on the right-hand side since the cosine A times cosine B terms subtract out. Note that if we added the two equations, we would end up with the third formula. Finally, we divide by 2 or multiply by 1/2 on both sides to get Formula 4. Again, notice if we added the two equations, we would get the third formula. Formulas 1 and 2 can be derived by adding or subtracting the addition and subtraction formulas for sine. Now let's consider an example using the formula we derived. Simplify sine of 15 degrees times sine of 75 degrees. We will use the identity for our sine A times sine B, which equals 1/2 cosine A minus B minus cosine A plus B. Now we substitute A equal 15 degrees and B equals 75 degrees in the formula. We simplify and note that both 60 degrees and 90 degrees are special value angles. Finally, we simplify to get that sine of 15 degrees times sine of 75 degrees equals 1/4. Let's consider a second example. Convert the product sine 4x times cosine 3x to a sum. At this point, it isn't clear why we would want to make such a conversion. It turns out, however, in calculus, that integrating products is quite difficult, while integrating sums is much easier. This time we'll use the formula sine A times cosine B equals 1/2 the sum of sine A plus B and sine A minus B. We substitute A equal 4x and B equal 3x into the formula. Then we simplify. Finally, we distribute 1/2 to get a sum. It's important to remember that in some situations the product on the left-hand side of the equation is preferable, and in other situations the equivalent sum on the right-hand side is advantageous. Let's consider a third example before we move to the sum to product formulas. Simplify cosine of x plus pi over 4 times cosine of x minus pi over 4. Simplify is a somewhat vague directive. We know we want to rewrite the expression, but what constitutes simpler depends on the situation. Perhaps we can at least do something about the pi over 4 terms. We will utilize the identity cosine A times cosine B equals 1/2 cosine A plus B plus cosine A minus B. We'll let A equal x plus pi over 4 and B equal x minus pi over 4. Then A plus B equals 2x and A minus B equals pi over 2. Now we substitute into the formula. We get the product equivalent to the expression that we can now simplify. We know that cosine of pi over 2 is equal to 0. Therefore, our original expression simplifies to 1/2 cosine 2x. As I mentioned earlier, sometimes it's advantageous to change a sum or difference to a product. Thus, let's consider the sum to product formulas. As usual, we'll state the formulas, provide one proof, and then illustrate via examples how the formulas can be used. The first formula equates the sum of two signs with a product. The second formula is for the difference of two signs. Notice the similarities between these two formulas. The product has one factor of sine and one factor of cosine. By the way, these are not the kind of formulas I recommend memorizing. Knowing they exist and being able to locate and use them when appropriate is probably enough. The third and fourth formulas deal with the sum and difference of two cosine values respectively. Notice that these formulas have products with matching factors and two cosine values or two sine values. We actually get these four formulas by clever application of the product to sum formulas we just discovered. Let's prove the fourth formula. This proof doesn't start with one side and work to get the other. Instead, we start with a known identity for the product of two sine factors. We will substitute alpha equal A plus B and beta equal A minus B. Then alpha plus beta is 2A, and A is alpha plus beta over 2. Similarly, alpha minus beta equals 2B, and B is alpha minus beta over 2. Thus, sine of A times sine of B is sine of alpha plus beta over 2 times sine of alpha minus beta over 2, and that equals 1/2 the difference of cosine beta and cosine alpha. Multiplication by -2 yields the desired identity, because 2 times 1/2 is 1, and the distribution of the negative reverses the order of the subtraction on the right-hand side of the equation. Now we'll consider 3 more examples, this time illustrating the product to sum formulas. First, simplify sine of 50 degrees plus sine of 70 degrees. We have an expression with two angles, neither of which is a special value angle. What does it mean to simplify this expression? We could either rewrite it as equivalent expression with only special value angles, or perhaps only one non-special value angle. Sometimes we just have to try a variety of solutions before determining which one is best. Let's use the formula for changing a sum of two sines into a product. We substitute alpha equal 50 degrees and beta equal 70 degrees in the formula. Next, we perform some arithmetic and are happy to see the special value sine of 60 degrees appear. We know that sine of 60 degrees is root 3 over 2 and that cosine is an even function. So the expression simplifies to root 3 cosine 10 degrees. Let's consider another straightforward example to write cosine theta minus cosine 5 theta as a product. We will use the appropriate sum to product formula, plug into the formula, and then simplify. The important thing here is to notice that there is more simplification possible. Since sine is an odd function, sine of negative 2 theta equals negative sine of 2 theta, and the two negatives effectively cancel out. Let's consider a final example in which converting a sum to a product is extremely useful. I will gloss over some of the arithmetic details here, but feel free to stop the video and fill in any missing details for yourself. We want to sketch the graph of y equals sine x plus cosine x, explicitly stating the amplitude, period, and phase shift. For our solution, we will rewrite the function using several identities. We start with the given function. It's a sum, but our sum to product formulas didn't include mixed sums. All of our formulas had the sum or difference of two sine values or the sum or difference of two cosine values. We can use the cofunction identity to rewrite cosine x as sine of pi halves minus x. Then, with the sum of two sine values, we can use the appropriate sum to product formula. We get 2 times the sine of half the sum of the two inputs times cosine of half the difference of the two inputs. Next, we evaluate sine of pi over 4 and simplify the other factor. Reducing yields that y equals the square root of 2 times cosine of the quantity x minus pi over 4. Now we can use what we know about graphing general cosine functions. The amplitude is square root of 2, the period is 2 pi, and the phase shift is to the right pi over 4 units. Therefore, we can sketch the graph by plotting a few convenient points and drawing the curve. If we want to sketch only one period of the graph, we would start our graph at x equals pi over 4 and end 2 pi units later at x equal 9 pi over 4. And we have a cosine graph with amplitude of root 2. The nice thing about this problem is that it uses a lot of prior knowledge combined with today's topic to sketch a graph that would otherwise be quite difficult to sketch.